Okay, starting the timer. Technology. Right, so we have questions. For assignment 2, the Brightspace due date is for the... What? Oh, that's a mistake. Oh, they've got some horn going. Okay, I can deal with this afterwards. Okay, the deadline for assignment 2 is Friday. Yeah, I probably got that messed up. It is like the coming Friday at the end of this week because, last Friday, because we need to have lots and lots of assignments in order to drop 2 of them. Right. So, I will email Sarah. Okay. So today we're going to talk about bounds. So asymptotic notation, the master theorem, upper and lower bounds, and the master theorem. So this, this is not sort of what I consider the most exciting stuff. Well, except the upper and lower bound stuff. Now that I've managed to sort of stuff that into this lecture, that I consider exciting. Okay. So first, you've probably all heard about the big O notation, right? I mean, you probably all used big O notation. Okay, I will email Sarah. Okay, for future reference, yes. If you have questions about something, email Sarah. I might be able to help you. You probably will be able to help you. Okay. So big O notation. People have seen, yes. People are saying yes. They've seen big O notation. Big O notation. Today I'm going to try to teach you what it actually means and how you should actually use it. But that's like teaching you exactly the proper ways to use it. Well, I'm not going to, for example, I'm not going to get into how do you use it with 2 variables because that's more complicated than you'll probably ever need to know. And actually, even the stuff I'm going to show you today, you don't really need to know exactly. I mean, in this class, yes, because if you don't learn it, I'll fail you. But once you get out into the real world, you're going to hear people saying things like, this takes at least O of whatever. And with luck, the stuff I'm going to teach you today, that's going to drive you nuts. Because it drives me nuts. It's like when people say, when people, you know how people say, she gave a cookie to Bob and I, and it should be Bob and me. Is it or say like Bob and me went to? It's like okay, like people. Yeah, I could care less. Is that kind of stuff? Like when people when they put apostrophes where they shouldn't put apostrophes. Like there's a cartoon that says if you really hate somebody, teach them to spot bad kerning. Kerning is the spacing between letters. Yes, that's an apostrophe. So I'm going to take that as an example, not as a message to me. Okay, so because there are things you should not say with big O. People tend to use big O for everything. They mean big omega and they say big O. And you should know what they mean. So I will do that. It's very hard. It's like using the subjunctive and stuff like that. Everybody makes mistakes. Okay. Big O means at most about. Big omega means at least about. Big theta means about. So we have, one of these days I'm actually going to open this new pack of markers. So we have Yeah, maybe I'm going to be opening the new pack. Oh no, there's this other pen. Okay, that's the very old blue pen. So big O of f of n means about f of n. Sorry. At most about f of n. Big omega of f of n at least about f of n. Big theta f of n about f of n. And then you have these little o and little omega. And those, they sort of mean, little o means sort of less than about. That's a bit harder to say it informally. Okay, so in the lecture notes, which I just uploaded, I started out by talking about my friend Simon, who is, he's a computer scientist, actually Simon, because he's German. And he's a runner. So he runs really long distances, very fast, not quite as fast as Turing. But let's suppose that he runs, the time he takes to run distance n is, I said, suppose Simon normally takes time n to the, what did I say, 7/8? 7/4 to run distance n. But Simon, he runs different speeds depending on whether he's had a coffee, or if he's got his favorite shoes on, or if he's tired, or whatever. So about this, times some constant. And we don't want to worry about these constants because who wants to keep track of whether Simon's had a coffee this morning? So suppose I run normally take time n to the, no wait, this was, Simon is 3/2 I think, and I'm 7/4. Okay, but maybe Simon gives me a head start, and maybe I have my favorite shoes on and he doesn't. So there's, this is some constant times this and some constant times this, and maybe I get, this is, he's going to give me a head start, so he's going to take n to the 3/2, c times n to the 3/2 plus 10. But you see that ultimately, if we run far enough, if we run for long enough, Simon's going to pass me, and then after that, maybe every so often he stops to tie his shoes or something, and I manage to catch up a little bit, but the functions are going to go, there's me, my distance, or let's say that this is, what do we want? We want time. No, we want time is the dependent variable in this. And this is the distance we run. And so I'm going to go like that. And Simon, Simon maybe starts out, he gives me the head start, and he's going to cross over, and then, So there's some wobbling around. We're going to cross, and ultimately Simon is faster than me. So my time is going to be, in the long run, Simon is faster. So you can see that regardless of whether or not he's had a coffee or whatever, Simon is faster. And so we want to be able to talk about ignoring things like head starts and shoes and coffees. And this is important in computer science because we don't want to care about, if we're talking about an algorithm, we don't want to talk about, yeah, that's, wait, but Simon is running, yeah, Simon is running at the 3/2, and I'm running, so I take more time to run, this is the time that I take to run distance n. Sorry, yeah, I originally was writing it one way, maybe I've messed it up in the course, in the lecture notes. But the idea is, because programs, we usually talk about time. We talk about the time it takes to process an input of size n. We don't talk about the time is fixed, how much of the input can we process. So that's why I flipped these around. So yeah, the distance here is n, and the time is some function of n. So, yeah, okay, don't need to draw. So, okay, we want to be able to say things like, in the long run, Simon is faster. And we don't care about constants, right? Because maybe I have another friend who's about as fast as me, and when you say about as fast, you want to mean like, yeah, okay, so depending on the day, depending on which shoes we're running, maybe one of us didn't have breakfast, you know. But, you know, you see what I mean, about as fast and in the long run for sufficiently long distances, for sufficiently large n. Okay, so, so first, wow, oh, this is way down here. I want to look at the notes just to make sure I'm not forgetting anything. Yeah. Oh, I can't believe I wrote all this stuff. I put all that cool stuff in about Turing. All right, so one way we can say this is that if my time is, so Simon's time is f of n, or, yeah. So Simon's time is f of n, and my time is g of n. So one way we can say this when we're saying about for sufficiently large n, we can say limit as n goes to infinity of f of n over g of n is 0. Okay? For sufficiently large n, the time it takes Simon to run a certain distance, it's going to be a negligible fraction of the time it's going to take me to run the same distance. So this is assuming that, well, okay. I mean, if it's a sufficiently long distance, then it will actually be exactly 0 because I will probably collapse before I finish. So it will take me infinite time. So what we actually, to say this, computer scientists, we don't do this limit stuff. We just say f of n, this is little o of g of n. Okay? Or equivalently, you might say g of n is in little omega that looks like a w of f of n. So this isn't at most about, this is actually, you know, a lot smaller than. And this is a lot bigger than, but for sufficiently large n. So O comes from the phrase in English, on the order of. That's a little bit misleading because we say, for example, N. Oh, and now I've gone and done this thing where I went and drew equals. And I actually wanted to draw set element. Okay, so N is an element of O of N squared. You've probably seen somebody write something like this. Okay, this is little omega. It looks like a cursive W. Would normally be the third notation. Third notation? Not sure. Okay, so this doesn't mean, if you say, in English, if you say on the order of, you'd be wanting to say like, oh, Travis runs on the order of the same speed as Simon. Well, it's true that Travis's speed is less than Simon's asymptotically, but it's not, roughly the same. So on the order of it usually feels like about the same. Like, oh, how long will this take, like on the order of 100 days? And if it then takes 2 days, you'd be like, well, on the order of it's like order of magnitude, the same order of magnitude. And if it took 2 days, you'd be like, yeah, well, it was big O. It's not going to work. So the origins of why this is big O are a bit misleading. Oh yeah, okay. Please. What is little omega? We're going to get to that. Okay. So I have to keep switching back and forth because normally I practice before the class. I know it doesn't seem like that, but I actually do. I read over the notes, but I had a meeting this morning. Okay, so I was saying the thing we should get straight about big O and big omega and theta and, well, you just saw me, I drew equal signs here. I shouldn't have done that. People do, but then people put apostrophes in bizarre places. These things are sets, okay? They are not values. Well, a set could be a value, but okay, they are sets of functions. So what is big O? Well, big O of f of n, or let's say g of n, which is I think what I did in the course, in the lecture notes. Big O of g of n is a set of functions. Big O of g of n, it's the set of functions h of n, such that h of n is at most about g of n. But at most about, in this case, has a very specific meaning. Now, if people have done, I'll switch back to the chat. So switching back to the chat, people have done epsilon delta ball proofs in calculus, right? Where you say, for every epsilon, there is a delta such that within a ball of radius delta of this point, this is when you do limits, right? Anybody? If you're within a ball of delta, okay, but somebody said yes. So some people have seen this. So I feel like this is something similar, right? So there exists an n0. So this is like saying for every, in epsilon delta ball proofs, it's like for every, excuse me, t. For every epsilon, there exists a delta. Looks a bit backwards. But actually, it's closer when we get to the definition of little o, which makes sense because I just showed you that little o it can be defined in terms of limits. So there exists an n0 and a constant c greater than 0, such that for all n greater than or equal to n0. So this backwards e means there exists. Or in this case, there are two things, so there exist. This upside down a, okay, so let's make it bigger. H of n, H, not n of n. There exists an n0 and c greater than 0, such that for all n greater than or equal to n0. So, have people seen this in logic? Okay, maybe I need to move this closer. Discrete. I'm not sure how much closer I can move it. Because if I move it too close, you can't see the whole board. Okay. There exists an n such that for all n greater than or equal to n0, h of n is less than or equal to, I forget if this is, I forget if it's usually a greater than or equal or just a greater than, but it doesn't matter because you can always choose your n0 plus a little bit. And this, I forget if it's a less than or a less than or equal, but if you want it to be a less than, just choose your c a little bit smaller. Okay. C times G. Okay, so it's saying that for sufficiently large values of n, so there exists an n0 such that once you get past that n0, then for all of these, h of n is less than some constant times c of n. So maybe h of n is actually bigger, but it's at most going to be, for sufficiently large n, it's at most a constant factor bigger, right? You'd be like, well, it's not less than g of n, but it's always less than 5g of n once n is bigger than 100. Okay, so this is saying for sufficiently large n, and this is saying this is the at most about. This is a dot. This is a period, not. It's just when people write the exists for all, they terminate the quantifiers with a period. I forget if they terminate every quantifier with a period. Somebody asked, is that a multiplication sign after n greater than or equal to n0? Okay. Oh, and I was saying that the reason we want to say that, the reason that for running, you want to be able to say Simon, Travis is slower than Simon, for sufficiently large distances, plus or minus up to constant factors. Well, actually, Simon is just much faster. We want to talk about this because if you change your computer, you add more RAM, the thing gets a bit faster. You use a different programming language, the thing gets a bit faster or slower. You hire a slightly better programmer, maybe the implementation gets a bit fast. You can do all of these things and it changes stuff by constant factors, and we don't want to talk about that when we're comparing algorithms. We also don't want to talk about like, insertion sort is faster than merge sort when you're really dealing with small instances. We don't care about that. So we want to be talking about like, okay, ignoring constant factors that change based on your computer and ignoring small instances, we're saying that O of g of n is the set of functions h of n such that there exist n0 and c greater than 0 such that for all n greater than or equal to n0, h of n is less than or equal to c times g of n. So For sufficiently large n, h of n is at most a constant factor times g of n. Okay?